Hello, everyone. I'm going to talk about types in Ember. I am Paul Steckler, and this is work with Matthew Ryan. We are both from O1 Labs in San Francisco. And types in Ember is about our library that we've written called PPX version. It's an OCaml library with 3 different pieces. One piece is a deriver for type declarations. We also have a transformation on modules and a linter on abstract syntax trees. And the goal of this library is for us to be able to version serialize types. And when we've done that, those versions never change over time. And that this achieves a kind of forward compatibility by default, so that when we create new versions, we can continue to use the old versions of types. Okay, the pretext for writing this library is we've been doing work on Coda, which is a cryptocurrency and application platform, and it uses the method of zk-SNARKs, a kind of zero-knowledge proof system, to prove the validity of our blockchain. And we're using, our Coda is using a proof-of-stake consensus mechanism, and those 2 features, the zero-knowledge proofs and the proof-of-stake mechanism, make it so that Coda has dramatically lower energy requirements, storage requirements, and the network bandwidth requirements when you compare it to other blockchains such as Bitcoin. And like other cryptocurrencies which live on the internet, there are communications between nodes. So one form of communication is a node will gossip blocks in the blockchain to other nodes, not expecting a response. But we also have RPC calls where we query, one node will query another node and expect a response back. And to perform these communications, we're relying on one of the libraries from Jane Street. It's called async RPC kernel, which uses yet another library called binprot, which serializes, gives a way to serialize and deserialize data. Besides the network communications, we also use serialized data to store, to persist data to databases. For example, we have this notion of an archive node, which we can store the entire blockchain in a database. So we have to serialize it first before storing to a database. So when we version a type, what does it look like? So here's an example from our code base. We have a module snark tables, and we have, that's contained within that is a module stable, and within that a version 1, v1. So this is the format that we borrowed from Jane Street, who stables some of their types in this way. We also, besides the basic structure here, we also have a function toLatest, which allows us to convert from a particular version to the latest version. Because we only have one version here, the toLatest is just the identity function. And you see the module alias latest is alias to v1. And outside the actual versioned module, we define a type T, which is the same as the type T in stable latest. And you see the 2 fields, all and rebroadcastable, are the same. The difference is that in the version type, all the constituent types are also versioned. So you see in the field all, we have ledger proof stable.v1, whereas in the unversioned type, it's just ledger proof.t. So we've embellished this kind of framework with a module annotation. You see that stable has this annotation versioned, and this allows us to omit the module alias, and it also allows us to omit the declaration of the type, the unversioned type T. So let me just flip back here. You can see that the module alias disappears when I go to the next slide, and also the type T at the bottom disappears. Oh, and I should also say The original type, we have the deriver binIO, which derives serializers, but we don't have to mention that when we add this version annotation on the module. Okay, so to serialize our data for RPC and for persistence, we're relying on yet another Jane Street library, ppx binprot, which allows deriving serialization code. So if I declare type t int cross string, if I add deriving binIO, that generates for me a reader and writer. And when we have used the version module annotation, it generates the deriving clause as we just saw in the 2 slides ago, but also some shadowing code. So the shadowing code shadows the reader and writer. The writer, when it writes serialized data, also adds a version number, an integer, before the rest of the serialized data. And if we want to read some serialized data, we have a function deserialize from binary opt, which takes a buffer of serialized data. It examines the version number in the that's been prepended and will invoke the reader corresponding to that version. And we'll also use the toLatest function so that we get an instance of latest.t. It's an option because the serialized data may have a bad version number. Either it's bogus or that version has been deleted from our code base. Okay, as we saw, when we declare a version type, we have a function. We need a function toLatest, which converts from a version type, say vn.t, to the latest, and we need to do that for each version module vn. There's some other mechanism for versioning that do some kind of automation between versions, but here we have to actually write out what toLatest is. But of course, that gives us, the trade-off is that we get complete flexibility. And when we're not writing code that converts wire data or reading persisted data, we're not using the version type at all. We're just we're going to be using the type t, which is defined to be the same as latest.t. So the only place you really want to use version types is when you're declaring other version types. Okay, besides the binIO deriver, we also, the version module annotation generates deriving version for that type, and that generates a bit of code, let __ version _ equal unit value, and that's just a marker saying, yes, this particular module has been versioned. And then when we're defining a type, if it refers to another version type, we generate a declaration that refers to that marker for that other module. And that enforces the fact that we have versioning for all the types that are involved. So if you haven't versioned M, it will be a compilation error because this definition, which refers to the versioned marker for that module, it won't exist. And so this scheme bottoms out at the OCaml built-in types like int and string, which aren't versioned. So we don't generate these kind of definitions for those types because those aren't going to change over time. Okay, so here's an example of what is generated by the combination of the version annotation on modules and the version deriver. So on the left-hand side, you see that we've annotated the module stable within transaction pool, and on the right-hand side, you see we have the deriving binIO and version, which doesn't appear on the left-hand side. We also have the definition of a value called version, which is 1 in this case because it's v1. That's automatically determined by the name of that module. Then we have the marker for this module. We have a definition which refers to that marker so we don't get errors like you've defined this value but you haven't used it. And then the two version types that appear within the definition for add and remove, they're the same. They're user command stable.v1.t. So we refer to we generate definitions, two identical definitions that refer to that marker for that particular module. Okay. Well, in some cases, our code uses external libraries, which haven't been versioned because, well, there's OCaml code that doesn't know about our library. So we have a variant of the module annotation called versioned asserted, and it generates the deriving version except with a flag asserted. And when that flag appears, we don't generate code to detect theversionness of the mentioned types. So we're asserting theversionness of this particular type. How do we know that it doesn't change over time? Well, we can't really do that statically. So instead, we require a test module in which we'll have tests that will compare against reference serializations. And to show you what I mean, here's an example from our code. We have a type called non-zero curve point compressed. We generate a value of that type using a quick check generator, and then we have a reference. It's actually a digest of the serialization because the serializations for a large type with lots of data might be very large, so we just store a digest of that. And then we take the module that's where we've asserted theversionness, in this case v1, and we're going to compare the digest of a fresh serialization against this known good digest. So check serialization will serialize this value using the bin.io code in module v1, and it will create a new digest and compare it against this reference digest. And if they differ, there's an error. So this is using the PPX inline test from framework from Jane Street also. And I'll hand it over to Matthew now.
Thank you, Paul. In some cases, we also need to create stable versions where we don't have a serialization directly. For this, we have the version Binable annotation, and it allows you to use the Jane Street core binable.of binable. This has an additional restriction where the of binable type, here the string.stable.v1 module, has to be a versioned module to ensure that we are still using versions correctly. We also provide a deriver for signatures, so that in the same way that you can define your version types in structures in modules, you can also define them on your signatures, and those matching annotations will do the corresponding manipulations so that the signature matches. The majority of our uses of version types end up in the RPC calls that Paul spoke about earlier. For these, we defer some of the versioning to the Jane Street async RPC kernel library, but we still support and restrict versions on these as well, using the version RPC annotation that you can see here. These are the root types, and so no other types should refer into them, but they are used both the query and response to communicate over the network, and so have to be versioned carefully. For each RPC version, we provide coercions between the caller and callee models, so that different callers and callees can negotiate the latest version when they're communicating. We also provide a linter. This ensures that when the deriving list includes bin.io, it must also include version, which will run the checks that all of the types included are version themselves. Also, these derivers must only appear in version modules according to the linter. Inside the version annotated module, you can only have modules named vn for some version number n. and version modules can only be used to define version types. For binable functors, as we saw before, the module argument providing the serialization must be a versioned module. In addition, while designing this, we found that functors were a dangerous pattern. For example, you could create an alias that wraps a functor, which creates a version type. But if it depends on its argument type, then changing the argument may change the version types opaquely. This hasn't been a problem for us in practice. We've disabled version types within functors, and we move our version types outside of the functor where we need to use bin.io. The PPX interacts well with editors. As you can see here, this is Emacs running, noting the error where you've attempted to create a version type within a functor. The highlighting shows you exactly where the error is and gives you a nice warning at the bottom. And similarly here, we check in the linter that versioned types aren't used outside of version modules to make sure that we're always using the latest type in code that shouldn't care about the particular version. In order to keep track of our types so that we don't inadvertently change them, we have a version of the deriving version PPX that outputs all of the version types in a project. We run this on our CI system, and it prints out all of the version types and compares them from the source branch to the destination branch. Any existing types should not change. The CI will fail if they have. We also found a need for a paradigm escape hatch. For example, some features that are self-contained, like visualizations or communications within the same binary. We don't need the versioning infrastructure when serializing them. For these things, we have to be careful, but we provide a bin.io unversioned deriver. It's backed by bin.io under the hood. And you can see here an example where we're using visualization data that will be used directly by the program. A bit of history on the development. We started using Jane Street style versioning on the RPC types. All of this was manual work, and there were a lot of types involved. This proved to be quite unwieldy, error-prone. It was often the case that we would change version types without realizing it. So we needed automation. We started with the deriver, which was a functor that you could use to add the annotations to the version modules and types. And then extension points to the rescue, we started building out PPX and came to the point we are today. So you can find a PPX version currently on GitHub in the O1 Labs repository. We're not on OCaml yet. We currently only support version 4.07.1. We're hoping to increase that support to later versions and push out to OCaml. You can find the Coda repository at this link here.